we want to make sure we're good, but not too good. We wouldn't want to replace what Brett does. He does an amazing job out there, and we would hate this. You know, we would hate to get more likes and viewers than Advanced Refrigeration Podcast. We do appreciate the Advanced Refrigeration Podcast.
That's right,
guys, for coming and hanging out with us during the AHR Expo. Thank you guys for coming to the Sporlan booth. It's always a good time getting to see Brett Wetzel and Kevin Compass. So thank you guys for coming out. So John, this is our day 2 of AHR. What do you think
already.
so far? Any thoughts?
I think it's going great. I think it's been a great show so far.
Yeah, we've had a lot of good participation. A lot of people come by the booth. Thanks for coming by today. I've heard a little bit of weather back home, so that might be.
Yeah. Sounds not quite as nice there as it is here.
Yeah, it's definitely been a lovely 70 degrees.
Or 80s.
Sunny,
yeah.
80s.
Not that we want to rub that in on the folks back home or anything.
No, not at all. So we're here today to talk about data centers. So why at the HVAC&R conference would we want to talk about data centers?
Well, data centers need cooling, and the more power that they consume, the more cooling they need.
Cooling's good. Cooling's good. We're in the
Very
cooling
good.
business, so that's always
very much
an
so.
important piece.
Yep, very much so. So there was recently, back a little less than a year ago, there was a study that estimated that data center power demand will grow by 160% between now and 2030.
Wow.
5 years. 160% increase in 5 years.
That is that's impressive. So how are they handling that kind of demand of increase in?
Yeah. So, more power means, more processing power means more need for cooling, because ultimately it's all dissipated as heat.
Yeah.
So, as we look at the things that are going to be required to cool data centers in the future, a lot of data centers today are cooled by air, forced air.
Okay.
That works at current power levels, but we're already starting to get past the power levels that can be effectively cooled with air. And that brings us to things like cooling with liquid.
Liquid cooling. Now, liquid cooling, aren't we? Electronics and liquid, that's not gonna mix well. What do we do there?
You have to be a little careful mixing those two things. You have to keep the heat transfer surfaces have good integrity. We'll say it that way.
Okay,
So
that sounds good.
you don't want to be leaking liquid, but the single phase liquids and electronics don't mix too well. But if you happen to get a little bit of refrigerant on your electronics, that's usually not such a bad thing.
That is a good point, John. It's actually was quite interesting. I was at a data center conference earlier this year, and I watched one of the gentlemen pour out a cup of refrigerant on the top of his laptop to show that refrigerant is actually a dielectric. So
it very much is.
You will not short out any components. That's one of the beauties of refrigerant.
Mm-hmm.
So that's great to hear. I've also heard that when you're looking at a data center cooling rack, today or in the past, they've needed to dissipate heat of about 4 kilowatts. And now with some of these, chips from NVIDIA, they're talking about 12 up to 30 kilowatts of power consumption by those chips. So that's a lot of heat.
That's a lot of heat. And in the future, they're projecting to go to higher numbers than that. So those numbers, 12 to 30, are actually probably near future.
Yeah. So you mentioned it a little bit. Liquid cooling is sort of the future for data centers. Obviously, there's the air cooling. And actually, before we go there, I wanted to hit on that's one of the reasons why it makes sense to talk about data center cooling here at the AHR Expo, isn't it? I mean,
it is.
Here at Sporlan Division, we've been involved in the air side of cooling computer rooms for a long time.
Yes.
Yeah, that's great. So what kind of what do they do for the air cooling today?
So for air cooling today, you have to, depending on the environment the data center's in, the air has to be filtered very well. because you're bringing in a lot of outside air to do it with, obviously. So it has to be filtered very well. But a lot of that air has to be cooled as well. If you're in, in a hotter environment, you have to cool that. And the rooms themselves, the computer rooms themselves, need to be air conditioned. And of course, air conditioning has been one of our core businesses for many decades.
Yeah, yeah. And I think that's one of the great ways that Sporlan Division is poised for the future in data center cooling is we've been involved on the air side, and all of the same customers and
Yep.
challenges with data center cooling. We're already there working with the same people, talking to the same people.
Yep.
But tell me a little bit about what this means. Single phase. I hear two-phase cooling.
Okay.
So what is this liquid cooling all about?
So liquid cooling can be, as you said, either single phase or two phase. Single phase is where you use, typically it'll either be a water and propylene glycol mix, or sometimes it can be just an inhibited water coolant to circulate through cold plates on the different components, directly on the chips and other components that are generating heat. And single phase can work pretty well. It's a big step up above air cooling.
Yeah, yeah.
It's still, it's greater efficiency than air cooling, more effective than air cooling, but you still have limits.
Yeah.
Single phase means that you're working with a pumped, like I said, a pumped water or glycol mixture. It's much less noisy. You start thinking about all the forced air, and you can get some really high noise levels. There's some high noise levels.
Yeah, I was just going to say that we have high noise levels at here, but this year it
doesn't sound like a fan, but
fantastic because we do have this nice podcast booth that gives us a little bit of a glass shield between the people out here, but you could still hear things because we're obviously in a very large hall here in Orlando.
In a trade show, and we have trade show sounds.
And we've got people talking and doing demonstrations all around us.
Yeah. But still, even single phase is going to extend equipment life. But you do run into issues because that's sensible heat transfer. So as you circulate that single phase fluid across the chip, it's going to gain heat, and it's going to go up in temperature. And so, to keep the delta T's down, you would have to keep increasing flow rates, and keeping increasing flow rates comes with a cost. It comes at a cost of pumping power, comes at a cost of increased component sizes.
Yeah, yeah. And we've been in some discussions with some of those different hyperscalers, as you call them, that are, working on new data centers. And a lot of them are talking about they are doing liquid cooling, and they're kind of maxing out at some of the capabilities on liquid cooling. And they are looking at increasing flow rates on the propylene glycol water side, sizing larger components, sizing larger pumps so that they can push more water through that. So then as they hit those upper limits of water, where do we go next, John?
From there, the next logical step is two-phase.
Excellent. Excellent.
And so with two-phase, you're basically going to use a refrigerant. You're going to use a type of refrigerant that's going to be similar to, but maybe not exactly the same as you'd use in maybe like a chiller application.
Okay.
Some of those things are very similar applications. So that might be what you'd use.
Yeah, yeah. There's a lot of chillers in data centers now. And then as we move to a two-phase, and we call it a pumped two-phase because we're pumping the refrigerant to the cold plate. And as I understand it, you're pumping it out through a system of connections and a manifold that goes onto the cold plate. And the cold plate sits right on top of the chips, the computer chips, the graphic processing units, GPUs or CPUs that need to be cooled. And it runs that refrigerant right over that cold plate.
Right.
And so then does the cold plate almost act like an evaporator in the system, or how does that work?
It does. It's equivalent to an evaporator in a vapor compression system. And you are boiling off refrigerant in there. Typically, you would not boil it off completely. You would bring pretty much a saturated liquid in, and you would bring a mixture out that's maybe 70% quality. So in other words, you boil off about 70% of the liquid.
Okay.
You leave a little bit of the liquid in there because that's going to help the return. You need some liquid in there to effectively return that mixture back to the pump and the heat exchanger.
Yeah.
Where
Yeah.
you're basically gonna run it through a heat exchanger that's going to recondense that refrigerant back to a liquid
Okay.
and then pump it out again. So it does not involve compressors and condensers like the full, like a full
vapor
compression.
compression cycle.
Right.
Yeah. Yeah.
But the advantage is, as you in the same vein as an evaporator, as you boil off that refrigerant across the cold plate, that refrigerant remains at the same temperature as it boils off, and so you don't have cool on one side at the inlet and getting increasingly warmer and warmer on the other side at the outlet.
Okay.
It's going to maintain the same temperature across there, and taking advantage of the latent heat transfer, you actually get greatly increased capacity out of that, because a lot of these refrigerants do have really great volumetric capacity.
Yeah. Latent heat exchange. That's the important one there. And
we just went right into the weeds, didn't we?
Yeah. Latent heat exchange. So that is why a pump two-phase system works well in the data center world.
Yep.
And I know that a lot of people are out there looking at data center cooling, and actually Parker Hannifin as an organization, as an enterprise, has been doing a lot with both single phase cooling. Yep. And when some of these same customers, some of these same people are coming and talking to Parker about single phase, and they're saying, what about two phase? That's where they get us involved, right?
Right. So with our background, that's where Sporlan Division has a big advantage in being able to help the customers that want to go the two-phase route.
Yeah, yeah. So I know that I get this question often, but when we talk about pump two-phase refrigerant, the next question I get is, so what refrigerants are we talking about?
So if you look at these types of applications, these are not exactly brand new applications. There's been at least a small portion of electronics cooling that has for years now used refrigerants in some way.
Okay.
And the kind of go-to over the past decade or so has probably been R134A.
Yeah.
That's one, that we're all familiar with. That's been a very widely used refrigerant over the last 30 odd years.
Good. And tried and true refrigerant. Yep, there.
It works.
Yeah.
But it is an HFC. It's relatively high GWP. And of course, there's a lot of focus on global warming potential of refrigerants legislation in the U.S. and really all over the world that helps to that's really phasing those higher GWP refrigerants down. And so now we have some of the newer HFOs that could potentially be applied in these types of applications, either by themselves or in blends. So you have things like R1234YF, R1234ZE, and then we have a very low pressure refrigerant, R1233ZDE.
Okay, R1233ZDE. Mm-hmm. Yeah, I've heard about that one. So what kind of pressures does that one operate at?
So 1233ZD is actually a very low pressure refrigerant. It would be, it's atmospheric, if I recall, at around, I want to say about 64 degrees F.
Okay.
So in other words, you could probably have a cup of it in a 64-degree room, and it would just sit there.
It would just sit there, wouldn't boil up.
Maybe bubble just slightly.
Yeah.
Wouldn't do much. But yeah, it's that's how low a pressure it is. So it would be essentially, 14.7 degree or 14.7 psi G.
Yeah.
Psi A.
Yeah.
0 psi G.
PSIA. Yeah. Make the atmosphere, not
right.
gauge. Okay. Right. I've got it. So then, as we look at those refrigerants, what other? So those are low pressure refrigerants. Right. I've also heard something about medium pressure refrigerants. Are they looking at any medium pressure refrigerants for data center cooling?
Yeah, absolutely. So I think it depends somewhat on the actual application. But the ones, a couple of the ones I just mentioned, the YF and the ZE, the HFOs, those are sort of medium pressure by themselves.
Okay, those are already. Yeah, my mistake.
Right, but those are also A2Ls, so they have some degree of flammability to them.
Gotcha. And we are very familiar with A2Ls, obviously, in this industry.
Yes, we are.
We've
Yes, we
talked
are.
about A2Ls a lot. There's been a big A2L transition on the residential and commercial AC side. We're looking at a transition on the commercial refrigeration side. But you know what? The people in the same people that are doing that aren't always the same people in the data center community. So A2L may be a little bit newer to some of those in the doing data center cooling.
And some of those applications, there's going to be quite a bit of these products in the data center. And so having an A2L may not be the ideal situation in a larger charge application.
Yeah.
So there are a couple of blends out there that use some of these HFOs to keep the GWP down.
Okay.
And use a little bit of HFC in them to keep the flammability down. So we have R513A and R515B as HFO, HFC blends that make the cut, so to speak, on GWP limit, but that are an A1 refrigerant that has good capacity and honestly act a lot like R134A would act in the system.
All right.
Yeah.
So that's a lot of good information on refrigerants. Would you say if you were to look at the industry now, and I would say it's still a burgeoning industry, it's still a new industry far as the pumped two-phase refrigerant data center cooling. I think we're still on the leading edge, but are there any, one or two refrigerants that seem to be more popular than others as people are testing their data center cooling out with refrigerant flow?
I would say probably the number one possibility, the highest interest we've seen is probably R515B.
Okay, yeah.
And then some interest in 1233ZD.
Yeah.
Just because of its low pressure design requirements. So you could have a system designed, the maximum pressure design for 1233ZD could be, in the range of maybe 75 PSI. And that would take you up, to some pretty high temperatures. And so that's kind of attractive, especially on a smaller system.
Yeah, that works well. And actually, John and I were talking to some refrigerant folks earlier this day, and they had made the comment that the 515B, the medium pressure refrigerant, they have tested it out in some labs and found that there is a 40 to 50% increase in cooling efficiency over water. So that's where we go back from the single phase to the two phase. When you're able to use a medium pressure refrigerant like a 515B, they've seen as well as a 40 to 50% increase in efficiency in cooling their system.
And that's impressive, when you think about it. I mean, water's an excellent cooling medium, but when you get past the what you can do, like we just discussed, when you get past what you can do with water, this really takes you a lot farther. It's not a little farther; it takes you a lot farther down the road of being able to run these higher power chips and deal with the heat.
And I think that's excellent because as you look at chips and the chip makers, it seems like almost every 6 months they're coming out with a new higher capacity or a new chip. And so I think at Sporlan Division, using some of these refrigerants for data center cooling can really help lead them into the future with some of that.
I think so. I think that opens up a whole, new set of possibilities. And when you look at we talked about this, potential 160% increase over the next 5 years. When you think about what that's being driven by, it's being driven a lot by AI.
Yeah.
And
for
those
sure.
types, those GPU type chips that they use for those, they're amazing chips. I mean, they're, something that you could hardly conceive of just a few years ago, the power, the things that they can do.
Yeah.
The computing power, but along with that goes that power density and the cooling requirements.
The cooling requirements. So, and that AI has just been explosive. We've got, all sorts of different AI systems out there. And I think really that's going to be a real big part of how we do business and how we do life in the future, whether it's Chat GPT or one of these other types of AI systems. So
I would agree. It's going to have a huge impact on our lives.
Yeah.
It's going to be a big part of our daily life going forward.
You know what I need? I just need AI to help me find my emails. If I could just have AI tell me where that email is buried and which folder I buried it in so that I can go back and refer to it.
I would say that would be a great application for AI. I could use the same thing.
Yeah. Sometimes that takes me longer than anything else. So
Yeah, yeah. The wonders of electronics and computing, and then the needs to deal with those. So yeah.
yeah. So as we talk about data center cooling, let's get into the nuts and bolts, the infrastructure side a little bit. As we talk about a cooling distribution unit that's going out pumping two-phase refrigerant to the system, what do we have here at Parker for hoses and fittings that can help do that?
So with Parker, we offer all sorts of flexible tubing and hose. A number of those hoses and fit and tubing, they are approved for use with refrigerants. We have some that have been specially developed for those applications.
Yeah, yeah.
So you have those lines. There's going to, of course, be some hard lines in the system here and there as well. But then you think about how a server rack and system is set up. They need to be able to change out blades and modules in that server very easily.
Yeah, they call it hot swapping, I
Hot
think.
swapping.
Yes, yeah.
And so you need couplings to be able to quickly disconnect and connect those blades as you take them in and out of the cabinets. And so there are couplings that we've offered for actually decades that are a good application there.
Yeah.
But there are some optimizations, some tweaks that we recognize we needed to make to those to try to make them even more friendly to the data center environment.
Yeah, that's exactly correct. And you're referring to some of our 5400 and 5500 series quick disconnects that are tested and been in systems with refrigerant on split systems and stuff like that for decades. And now we have a new, what we are calling the quick thread quick disconnect. And the advantages there are that it's almost 70% quicker in connecting and disconnecting. It is a threaded connection design, and that is because when you are working with some of those medium pressure refrigerants like a 515B, you need to mechanically overcome the pressure. If you have, 200, 300, whatever it is, pounds of pressure in your line, when you need to connect and disconnect, you have a way of needing a mechanical advantage to connect your quick coupler, your quick coupler. And so that's why it's a threaded connection, but it only takes, I think, 2.5 or 3 turns to connect. So it's very quick.
It's real quick.
You can do it without a tool, which is great. No tools needed. And they are able to fully disconnect and hot swap. They're able to take out their servers and change them out.
Right.
And also, John, I was told by some of the really smart engineers, much like yourself, is that we can even pull full vacuum on a disconnected quick coupler. So pulling vacuum, I've been told, is important in a system because you need to service it. If you want to, charge the system, you need to be able to pull a vacuum.
Right. So as those components would go in, you don't want to be putting them in with air or incondensables, or worse yet, any kind of residual moisture that may be in the lines.
Yeah, that's important.
Yeah, you want to be able to pull a vacuum on those components before you put them in. You want to be able to, exactly, just for serviceability, to be able to pull vacuum on sections of the system and not have to worry about leaks at the couplings. And so that's one of the big advantages of all these couplings, is they're fully vacuum capable.
No, that's fantastic.
No issues there.
Great. Well, I appreciate the time today and talking about it. So data center cooling is definitely a new emerging trend, and I think we're going to just see it over the next couple of years to grow even bigger. And as we move into the liquid cooling, that'll be more advanced. And as we go into higher needs with liquid cooling, we'll definitely need a 2-phase cooling system where we'll be refrigerant cooling. And obviously here at Sporlan Division, we've working with the broader Parker folks to come up with manifolds, with hoses. And then at Sporlan Division, we have the quick couplers to do the quick disconnects on the refrigerant flow. And then also we have other components too, right? Filter dryers and ball valves, solenoid valves.
Things for, filter dryers, as you mentioned, for contaminant control. It's a great way, if you do get any kind of, particulate matter or moisture introduced in the system, they can very easily, be removed with catch-all filter dryers. And, there are a few other things here and there additional things we may be working on as well. So, can't talk a whole lot about them today, but there might be a few other things that we have in mind
Okay.
for this market.
Stay tuned. There may be future podcasts in out there on the Sporlan side that's talking about new things. So
I think there may be.
All right. Always like that. We got to leave the crowd wanting more. So thank you for your time today, John. I appreciate it. Thank you for taking a little bit of time to talk about all the new advancements with data center cooling. So with that, we're signing off. We'll call it the Ben and John Show. Thanks very much, everybody. All right. Thank you. Bye.